Okay, our next example of a descriptive statistic is the standard deviation of a data set. Standard deviation is a considerably more subtle notion than that of the mean, but the two are related. And in fact, the term standard deviation is really short for standard deviation from the mean. The mean, as you know, gives us a sense of where the data's center lies. The standard deviation gives us a sense of how the data is spread around that center. Now, the formal definition of standard deviation is a bit tricky, but the basic intuitive idea is actually pretty simple. The standard deviation describes, roughly, the average distance of the data from their mean. Now, the precise type of average is where this gets tricky. As you know, the word average is ambiguous and needs to be specified here. We will fill those details in soon, but for now, let's just leave it rough while we build up our intuition. And we will start with two trivial examples. Suppose we have 30 students that take a test and their mean score is 75. Now, this gives us a sense of the center of the class, but it doesn't tell us anything about how the individual scores are spread around that center, that mean of 75. So let's consider two very different scenarios in which the mean could be 75 points. First, we'll suppose that every student earned 75 points on the exam. Well, what should the standard deviation of these 30 identical test scores be in this case? Let's think back through to our initial intuitive idea of the standard deviation. The standard deviation describes, roughly, the average distance of the data from the mean. This should tell us what the standard deviation here is. Since everyone scored a 75, no one varied from the mean at all. There was no deviation from the mean. Thus, everyone's individual distance from the mean was 0. So the average distance from the mean was 0 too, and hence our intuition guides us to the correct answer that the standard deviation in this case of the data is 0. Now let's try scenario 2. Here, half the students earned 50 points, while half earned 100. A very different situation indeed. Instead of everyone doing pretty well, half the students had perfect scores, while half failed. Still, the variation is simple enough in this case that we can still guess the standard deviation without having to do any elaborate calculations. So we ask again, what is the standard deviation in this case? Well, we will think again what the standard deviation is supposed to tell us. The standard deviation describes the average distance of the data from the mean. In this case, every single test score was 25 points away from the mean. It was either a 50, which is 25 points below the mean, or 100, which is 25 points above the mean. So it should come as no surprise that the standard deviation from the mean of this data is in fact 25 points. These last two examples were unusually orderly. Real data obviously isn't like that. It's usually spread around in a much more haphazard way, with some data close to the mean, some data far away from the mean, some above it, some below it, and so forth. To see how we compute the standard deviation in general, let's work with a much smaller data set. Let's think of these as 5 test scores. In practice, it would be silly to compute descriptive statistics for such a small data set, since it's easy to understand all by itself. Nonetheless, it will be easier to follow the logic with only 5 data points than with, say, 500 data points. The process will be the exact same either way. So we are now marching towards the standard deviation of this particular tiny data set. Since the standard deviation measures average distance from the mean, we had better begin by computing the mean itself. And this turns out to be, as you can verify, 73 points. Now, remembering again what the standard deviation means, that in some sense it is the average distance from the mean, we are going to put a second column on this table, and this column will give us the distance from the mean of each of the 5 data points. Let's look at the first one, for example. It's a score of 80. Now, our mean score was 73, so 80 is 7 points above the mean. So I'll put a 7 here in its distance from the mean. 70 is 3 points below the mean of 73. So I'll put a -3 here. It's 3 points under the mean. 60 is 13 points below the mean, so it'll get a -13. 70, once again, is 3 points below the mean. And 85 is 12 points higher than the mean of 73, so I'll put a 12 in the column here. Now, what are we going to do from here? One reasonable idea would be to look at all of these distances and reason that since the standard deviation is supposed to be some kind of average distance from the mean, maybe we should just take the mean distance from the mean. And we can compute this in the usual way, but if we do so, if we carry out the arithmetic, we get 0. Now this is unfortunate, since 0 does not give you a sense for a typical deviation from the mean in this particular case. This suggests that the mean distance from the mean probably is not a very good way for us to define the standard deviation. We will have to find some other way of doing it, which we will in a moment. But I want to pause just to mention that something very interesting is actually happening right here. You might think that I cooked up these data to make this all work out to 0 just to make the point that the mean distance from the mean isn't a promising path forward. But this is not so. It turns out that if you take any data set whatsoever, compute the mean, then compute the distances from the mean as we've just done, and then take the mean of the results, you will always get 0. Always. I encourage you to just make up a few numbers on your own and try this for yourself. And those of you who are more algebraically inclined might wish to prove that this always happens. It's a good little algebraic challenge. But the problem remains. How should we actually define standard deviation? We know we want some kind of average distance from the mean, but the mean distance from the mean clearly doesn't work since it always yields 0. Two fairly simple ways to patch this up suggest themselves pretty naturally. First, you might notice that we ended up with 0 because the positives and the negatives in the distances from the mean canceled each other out. So why don't we just look at the absolute values of the distances from the mean and take their mean? They'll all be positive, so their mean certainly won't be 0. This is a good idea, but it is not ideal. The absolute value function has a corner in its graph. And if you've studied calculus, you know that calculus breaks down at corners. Now, we're not going to need calculus in this class, of course, but statisticians do want to have calculus at their disposal, so we don't want to define standard deviation in a way that shuts down calculus. The second fairly natural solution that suggests itself is to say, well, since we want some kind of average distance from the mean, why don't we just do the median distance from the mean? We could, but that too turns out to have all sorts of algebraic problems down the line, so we're not going to use that either. Instead, we have to do something that's a little more convoluted, but actually gets us what we want. We'll use the observation that it was those negatives, the negative distances from the mean, that were screwing us up. And the way forward is to recall that there's another way to turn negatives into positive numbers. Rather than taking the absolute value, we can square them, because if you square a negative number, you get a positive number, because everybody knows minus times minus is plus. So if we square all the distances from the mean, we'll get squared distances from the mean, and these will all be positive. So perhaps if we look at their mean, we will get something useful. Well, let us see. Let's start with the first data point, 80. 80 is 7 points above the mean, so its squared distance from the mean is 7 squared, which is 49. We'll do the same thing for all the data points. 70 was 3 points below the mean, so its squared distance from the mean is minus 3 squared, which is 9. Similarly, minus 13 squared is 169, minus 3 squared is 9 again, and 12 squared is 144. Now we'll look at all of these squared distances from the mean, and let's take their mean, so that we're looking at the mean squared distance from the mean, which is a bit of a mouthful. Nonetheless, we still compute it in the usual way. We add all of these square distances from the mean up, all 5 of them, and divide by 5. And when we do the arithmetic, we find that that is 76. Now, this value, the mean squared distance from the mean, is actually quite important in statistics. Sufficiently important that it has its own name. It's called the variance of the data. And the variance is a concept that we may touch upon later, but for our purposes, it's really just something we see out the window on our way to the standard deviation. The problem with the variance is that it's in the wrong units. Our data is measured in points, 80 points on a test, 70 points on a test, or what have you. The second column, the distances from the mean, are measured in points, 7 points above the average, 3 points below the mean, etc. The third and last column, however, is not measured in points at all. It's measured in square points. That means that the mean squared distance from the mean, in other words, the variance, is also measured in square points, which makes it not what we want. We want our standard deviation, since it's going to measure the typical distance from the mean, we want that to be measured in points, not square points. Fortunately, there's a very easy solution for this, and all we're going to have to do is take the square root of that number, which means finally we arrive at our definition. The standard deviation of the data is just the square root of the variance. In other words, the square root of the mean squared distance from the mean. In this case, it's the square root of 76. Let's put the units there as well. It's the square root of 76 points. So we've got the right units. Run that through our calculators. We find that the standard deviation of this little data set is about 8.7 points. So the moral of the story is, to compute the standard deviation of the mean, we look at the squared distances from the mean and take their mean. That gives us the variance, which is in the right neighborhood, but the units are wrong. So we take the square root of the variance, and that brings it down to the standard deviation. So it's a very peculiar kind of average. And now that we have worked out the computational side of the standard deviation, we need to talk more about getting an intuitive feel for what it means, for how to use it, and so on and so forth. And that's what the rest of this lecture will be about. To deepen our intuitive understanding, we want to think of a dataset's standard deviation as an intrinsic measuring stick. The idea is that every dataset has a built-in intrinsic unit of measurement that is somehow natural to that particular dataset, at least for the purpose of measuring variation from the mean. That built-in unit of measurement is nothing other than the standard deviation. When we want to know how far away something is from the mean, instead of saying it's 10 points above the mean, or 20 feet below the mean, or 14 seconds above the mean, we'll often find it useful to say it's 2 standard deviations above the mean, or it's half a standard deviation below the mean, or 1.3 standard deviations above the mean, and so forth. Anyway, a few concrete examples should make this clear. First, let's consider the heights of all men in the USA. Now, the mean height for American men is about 5'10". It's actually slightly less than that, but I'm rounding up to the nearest inch to keep our numbers clean. I will put that mean value on the number line. And now to set the scale on the number line, I'm going to consider the standard deviation. Well, the standard deviation for men's heights in the US turns out to be about 3 inches. So the average American man, we might say, is about 5'10", give or take 3 inches. We're thinking of our standard deviation, remember, as a built-in measuring stick. So I'm going to measure off 1 standard deviation above the mean. Here, each standard deviation is 3 inches, so this takes us from 5'10" up to 6'1". Similarly, if I measure off 1 standard deviation below the mean, since each standard deviation, again, is 3 inches, this drops us from the mean of 5'10" down to 5'7". You get the idea. If I go 2 standard deviations above the mean, I move up to 6'4". And if I drop 2 standard deviations below the mean, I'm down to 5'4". We could, of course, go out 3 standard deviations or even more, but I'm going to stop here since you have the idea. Do note, however, that we've already captured most American men within 2 standard deviations of the mean, and that men who are outside of that range certainly stand out as unusual. If a man is more than 2 standard deviations above the mean, everyone thinks of that man as a tall man, and the same thing happens on the other side. If a man who is more than 2 standard deviations below the mean robs a liquor store, all the witnesses are going to describe the bad guy as a short man. Anyway, let's do one more quick example before we move on to some important theoretical results. Let us look at SAT scores. Among all the people who took the SAT last year, the mean score was 1,060 points. This is out of a 1,600-point scale. The standard deviation among the test scores was 195 points. So, once again, if we measure off with our intrinsic measuring stick 1 standard deviation above the mean, that signifies going 195 points above 1060, which brings us to 1255. And we do the same thing on the opposite side, which gives us a score of 865. 2 standard deviations above the mean brings us to a score of 1450. 2 standard deviations below the mean brings us to a score of 670. Note that just like in our previous example, by the time we've reached 2 standard deviations away from the mean in either direction, we're getting to quite unusual data. If your score on the SAT is more than 2 standard deviations above the mean, you're going to be admitted to every 4-year college in the state of Washington. On the other hand, if your SAT score is more than 2 standard deviations below the mean, let's change the subject. Who's that handsome man? Why, it's Pafnuty Chebyshev, the great Russian mathematician from the late 19th century. We're interested in him here because of something he proved known as Chebyshev's theorem. I'm actually going to show you a scaled down version of the full theorem, but that will suffice for our purposes. Chebyshev's theorem says that in every data set, at least 3/4 of the data lie within 2 standard deviations of the mean. Note the universality. This holds for every data set. No matter how strange your data, you can be 100% certain that at least 3/4 of it lies within 2 standard deviations of its mean. You might think that if you try hard enough, you could find a counterexample, some data set for which Chebyshev's theorem isn't true. You cannot. There aren't any. There never have been, and there never will be. You can prove this algebraically, though the argument is a bit too involved to present here. Anyways, let's make this tangible by looking at some concrete examples. First, to get some data, I have just pulled 40 books from one of my bookshelves and counted their pages. After the usual calculations, I found that the mean number of pages was 398, so I'll put this on the number line. And the standard deviation was 146 pages. So the typical book in this particular batch was 398 pages, give or take 146. If we lay our standard deviation ruler down a few times in the usual way, we'll get a picture like this. So what does Chebyshev tell us? He tells us that if we reach out our arms to cover everything within 2 standard deviations of the mean, we're going to capture at least 3/4 of the data. That is, at least 3/4 of these books must have page counts in this range. Even more specifically, since there were 40 books, and 3/4 of 40 is 30, Chebyshev is telling us that at least 30 of these books have between 106 and 690 pages. Do note the boldface. At least 30 of these books. It could be more, much more. It could be 35 of the books. It could even be all of the books. All that Chebyshev's theorem does is establish a lower bound, at least 30. And since I happen to have the books before me, I can tell you the precise number of books in this range. It was 39. And the exception, in case you're interested, was Moby Dick, which is 851 pages long in the edition I have. Well, let's consider one more example, which we have seen before. Men's heights in the USA. As we've discussed earlier, the mean height is 5'10". The standard deviation is about 3 inches. Measuring off a couple of standard deviations on each side, we get the following picture. What does Chebyshev have to say about this? Let's call him in. Chebyshev tells us that if we reach out our arms to cover everything within 2 standard deviations of the mean, we will capture at least 3/4 of the data. That is, at least 75% of all American men are between 5'4" and 6'4". And once again, that is just a lower bound. In fact, the actual percentage is much higher, as we will soon see. But first, we will need to introduce a new idea, one which is going to become increasingly important to us as the course progresses. Normally distributed data. We say that data is normally distributed when it falls into the following bell-shaped pattern. The idea is that most of the data is clustered around the mean, and the further you move from the mean, in either direction, the less data there is. Note also the symmetry. The data dies off to the right of the mean in the same way that it dies off to the left. Just as we can use the perfectly straight lines of geometry to study the physical world, even though there are no perfectly straight lines in the physical world, so we can use this perfect mathematically defined bell curve to study real data, even though real data is never perfectly bell-shaped, though it often comes quite close. There is in fact a mathematical formula for this bell, but you don't need to know it for this class. At any rate, now that we know what is meant by normally distributed data, we can turn to what is called the normal rule. Unlike Chebyshev's theorem, this isn't universal. It applies only, as the name suggests, to normally distributed data. It tells us that if a data set is normally distributed, then 3 things are true. First, approximately 68% of the data lies within 1 standard deviation of the mean. Next, approximately 95% of the data lies within 2 standard deviations of the mean. Note how this is a much stronger statement than Chebyshev's theorem. Chebyshev merely tells us that at least 75% of the data lies within 2 standard deviations of the mean. But if we happen to know that the data is normally distributed, then we know much, much more. We know that approximately 95% of it lies within that range. Finally, the normal rule also tells us that approximately 99.7% of the data lies within 3 standard deviations of the mean. Let's apply the normal rule to a particular case. Back to men's heights. These are indeed normally distributed, and as we've seen, the mean is 5'10" and the standard deviation is 3 inches. So let's start by putting the mean on our picture. And now let's go out a standard deviation on each side. That region contains approximately 68% of all men, according to the normal rule. Approximately 68% of all American men are between 5'7" and 6'1". If we go out 2 standard deviations from the mean, we're going to capture 95% of the data, according to the normal rule. That is, approximately 95% of all American men are between 5'4" and 6'4". And if we go out 3 standard deviations, we're going to capture 99.7% of the data, according to the normal rule. Approximately 99.7% of American men are between 5'1" and 6'7". It's only about 3 in 1,000 that are going to be outside of that range. And that, my friends, is the last thing I'll say in this lecture on standard deviation, except to remind you that he who understands standard deviation will not end up like this guy. See you in episode 3, when we will begin our study of probability.